All right, we're going to get started, I guess. My name is Eric Johnson. I teach at Laguna High School, which is just a public high school, in Elk Grove, which is just south of Sacramento. I've been teaching AP Physics for quite a few years, and somebody approached me and said, would you like to start a Green Energy Academy? Because that kind of become the new movement in schools. And if you look at where the government's putting their money in schools right now, they're putting in what are called academies. It's a CPA, a California Partnership Academy. You can be an ag program, a woodshop program, a culinary program. Well, we chose to start a Green Energy Technology Academy. And what we do is we look at technology and renewable energy. This freshman level look at pretty much all those energies on a small modular scale. So like solar, they do solar race cars and solar ovens. They might do a little wind turbine. They might do some digestion in like a 5-gallon tub or something like that. By the time we move on to your sophomore level, the projects are getting pretty complicated and big. The sophomore first term, what they study is solar. What they actually built was a PVC cart. They had a 55-watt panel, had the inverter, the charge controller, the battery, all those kind of things. That's changing into a solar case, which we'll be shipping over to like Africa and other places. We wrote some grants last year and got about almost $30,000 to build these solar cases. And the students coming in the end of October will be building these things. We'll be building 20. I'm sharing the money with other schools in the district. And another school has already built 20. And we have different humanitarian and missionary organizations that are sending these all overseas. They're going over to medical clinics. They're going into schools. And they're a learning aid. They're saving lives. The numbers are pretty cool. The second term, sophomore year, is large wind turbines. The kids build the turbines. They use a permanent magnet motor as a generator. They build the charge controller. The code for programming the chip is already done for them, so they learn how to actually just upload the code to a chip that's on the charge controller. Then they get into the junior year, and first term was alternative fuels. And up to this point, we've been trying to get to algae and turn it to biofuel. And last year, our attempts, you got a little bit of an oil slick on top of the water. It wasn't real good. And we started doing some research, and the companies that were supporting us were actually jumping ship. We're actually seeing that that movement of algae to biofuel just doesn't pencil out economically. We looked it up the other day, and it says currently it's $33 per gallon. It's like, well, okay. So midway through the term, we go, we've got to study some other alternative fuel source, and that's when the GEK comes into place. I'm not going to talk about that too much. We'll let them talk about that one. By the time they become seniors, they're doing independent research projects. We have a 1 kilowatt system that's been going on our system. We're going to be doing some evaporative cooling systems. We're going to be we're partnering with our Sacramento State University students and some industry partners and putting together some training videos for these schools I've made contact with over in Nigeria. So it's a pretty cool program. So with that, Kristen here is going to talk a little bit more about what they're doing this term in the alternative fuels program.
So this term, we explored different possibilities of alternative biofuels, which included the algae at first, and also the GEK and recycled cooking oil. We were actually able to take waste vegetable oil and turn it into usable biofuel.
You want me to talk to this one a little bit? Yeah. This one right here was really what we did last year. We actually had some bioreactors that we had built. We built 4 of them last year with the help of a company called Ternium Bioindustries. And the whole idea was to concentrate algae outside using this bioreactor. It's clear PVC pipe. And then at some point, we take the algae and stress it in terms of taking away nutrients or light or changing the pH or something like that. And then the trouble really was, how do you take the algae and get the oil out of it from the algae? We actually bought 4 different strains that were proven to create oil under stressful conditions. And so one of the ways was to actually put it into a solar trough under pressure. We'd actually heat it up, using the solar trough, have an enclosed vessel, put some of the algae water in there, get it to about 250 degrees, and then all of a sudden we would release that pressure, and that superheated water then would turn to steam, cap open the algae, and get us the fuel, or the oil at least. There was an electrical stimulation we tried, also taking the algae, drying it out in the sun first, and then putting it into a press. None of that produced any kind of significant amounts of oil, but conceptually it worked for us, but not real well. The flaxseed was going to run through a press, take the oil out, and all these actually lead to this biodiesel processor. This is sitting in my classroom right now. It's sitting with about 35 gallons of diesel in it, And where that really came from, the majority was waste vegetable oil. So we processed that through using the methanol and the potassium hydroxide. Problem is that you get, for building from 40 gallons of waste vegetable oil, you get about 17 gallons of waste glycerin. Well, the nice part is we saved that, and I think we can supplement the fuel going in the GEK with that glycerin. All right, possibly. We're going to think about that. We were donated a gas chromatograph, so what we can do is take the biodiesel that we've created, analyze our gas chromatograph, and we have a donated diesel engine here that we can run. It produces both 110 and 220 volts, and the only 220 we have to run this guy actually is from this generator. And this was last year's program. We started with it, but because of this huge change we found this year, we've moved on to, next slide. Next slide. There, now Kristen, here's
So we moved to the, okay, so we moved to the GEK, and what we would do was take biomass, put it in the shredder, and then we put it into the hopper. We take the syngas from the hopper, put it in the generator. From the generator, we create power. We take the power into an AC to DC converter, and we put it in a charge controller to a battery bank. And if we want to keep it DC, we just use the batteries, or we can use an inverter and get AC power. We use the flare-off. We connect the flare-off to our greenhouse to help with the heat. Also, we take the heat from the truck, and then we put heat up water, and then we use the solar top to heat up, even to make even more heat for the water to create steam. Then we use steam, and when it condenses back, we have pure water. And
Can they see those pictures? Can you guys see those? And I hit the I believe button. This is a picture of a 25 by 50 foot compound that we had built for ourselves. And this picture is showing nothing done. And you're going to have to believe me here. Here's the beginning of the greenhouse. There's a gated section that we built over here that's going to house the GEK. That's better. So this corner over here is this corner here. The kids have built that this term. The reason we're doing the greenhouse is because of the land that we were given over in Nigeria to run a greenhouse and raise the goats as a kind of a beta project, I guess, for lack of a better term. So I'm using my kids to actually do kind of an international piece. We'll get the greenhouse running, figure out what works, doesn't work, put a training video or lesson or booklet together, and get it shipped over with some of our teams that go over to Nigeria. Other stuff, go ahead.
So this is GEK. We got the hot toddy. When we knew we were going to move away from algae, we were looking for another thing that was getting big, and we saw that gasification was getting big. We talked to a guy named John Balachandra. I believe he was a professor at UC Santa Barbara. Santa Cruz, excuse me. And he was teaching, about gasification and its process, and we're like, cool, this is something we got to jump on the bandwagon. Then we found you guys who make these, and it was wonderful that we found this. So we started piecing it together, and it was just interesting because this looks like something that's promising, unlike the algae, which when you look at algae, it already starts looking like, this is a hard process to get to, our final stage where we can actually use it for energy. But then when you look at the GEK, the processes are, you can already see to your final result. You know what I mean? It's almost like, a straight tunnel. You can almost see the light at the other end. So, been working on it. We had some issues. Some of us, since we're still getting into this, we're still looking at to piece some of it together. Some of it's like, oh man, where does this go? So yeah, this is about how far we've gone on it.
Yeah, these pictures were taken this week, weren't they?
Yeah.
So this is the GCU, just the same that we use on every GEK. We have done some circuit boards before. It's in our wind turbine and our solar carts, but nothing this complex before. It was really amazing getting to use Arduino and see all the different temperatures, how it records from every second, how to attach the thermocouples and the pressure gauges to this. It was a new experience, and it was really exciting to learn.
That's kind of the shed structure. We kind of cheated here. We used the corner of the compound as one wall, another wall, then off the two existing posts. We built gates. We have a post in the center that holds the support structure, but that's how we're going to be. It's obviously outside, not inside the classroom because of the CO emissions and such. What's that?
So are you planning on using the GCU to control other processes in your
Eventually, especially my seniors, as they get into it. You know, Chris is going to be a senior obviously next year, so that'll probably be a senior project that she really digs into next year.
And that's what we had to build that because we couldn't find any existing processors in the microcontroller world that were relevant for the issues you have in thermal projects or in energy projects. Many channels of temperature and many pressure channels are not stuff that you deal with in robotics projects. Nearly any energy project is going to have temperature and pressure issues. So, any fuel-based one is going to have it. So.
Okay, so this is the help slide. So for you guys, these are the parts that we kind of don't know what to do with.
Well, we understand the auger.
Well, yeah, we get their use, except implying them into the actual design. We were kind of lost at. I guess the manual we got wasn't exactly our version. I guess we got a prior one, so we're looking at it and like, that's not there, Mr. Johnson. And I was like,
So you're saying you got some customer service issues?
yeah, well, maybe just a little bit.
Yeah, the
No.
problem is we change this stuff so fast we can't keep the instructions current. I think it's like better to ship the new thing than like kind of simple. Yeah, we know we have to update it.
So before we leave today, we'd like to identify and figure out how some of these cowling pieces, and we understand that, just a few of these pieces. Like,
They're easier to recognize.
Or did you guys have an instruction manual? I thought you guys had for each design for the
There
DIYs.
is actually the current one up for the V4.
But this is the V 3.5, if I'm not mistaken.
No, well, a lot of it overlaps, so I actually can't even tell from this.
Okay. Why? Is your V4 the stainless steel edition?
No. No, this is, you have a V4, you
Oh,
don't have
okay.
a 3.5. So if you're reading the, because this is the side shaped grade. So if you were reading the V3.5 instructions, that would have led to some confusion.
Oh, okay.
that's, I think, what we're looking at.
Yeah, just
Okay, so then that would be the core thing, because yeah, you have the grate fence. Yes.
They can point out the stuff in here.
Okay, well. So this here is the fence that holds up the grate. Up to the 3.5, that there was a rotary grate, there was a center post that the grate sat on top and it spun around. And we changed to a side-shaped grate for reasons of, it's easier to deal with the mechanization and automation in terms of the type of movement we wanted. It's a long story, I don't want to get all into that. And the ability to put the auger underneath to get the ash out was a problem with the post at the center. So we went to a side-shaped grate and also the hole through the side of the vessel that you can get in. So that's the fence that creates a ring around the outside that the grate sits on. There's four, you should have found some.
Stainless steel bolt to 4
Yeah,
button.
you screw those into that, and then that's a table that sits in the base.
Okay.
And that'll just push down inside the insulation ring.
And the one that Schaefer grates go right on top of it?
Well, this one, the one that has the
The
bolt
mold.
on the side that you put the rod in, there should be a grate, perf, that has a fence underneath it.
Yeah.
And then there's a big T-handle that you can screw in.
That T-handle was, the diameter was thicker than the hole. I was not able, it's quite a bit thicker.
Well, that was a manufacturing issue.
Really?
So you had both customer service and manufacturing issues. Okay, so we should give you another one. So yeah, that T-handle should screw into there. Okay, so that's the grate. And then these two are perf for your filter, the bottom and top of the filter.
For the wood. What did that device do right there? I don't know.
This goes on the bottom of the drawing bucket, from the bottom of the toddy, or the drawing bucket. The fuel's coming in the top and going in. The gas is coming in the bottom, going through it, and then coming out to the filter. So this is the bottom plate. That hose attaches down to the
Okay,
cycle.
and then you have the shorter steel bar with the threads. The shorter one goes on the end of that.
No. This goes into the bottom of the bucket that's underneath the hopper. And then there's a little orange hose that goes between.
Just hose, not the actual
this.
steel pipe then.
No.
Not the gas pipe. Okay.
No, so this goes from here to the cycle. Okay, which would be flipped over.
Oh, okay.
This is a insert that goes into the top of the reactor. We've been putting a lot of tapered inserts at the transition between vessels to improve the mechanical fuel flow. If you have a hard joint in a vessel, you will get an angle of repose that forms there out of the fuel. But the difference in that of fuel flowing down that angle of made out of biomass and made out of metal